Okay, and how about the distance? We can also require things about the distance function. So just about the distance function, we can require a space to be connected space. So, well, this also has to do with topology, but for example, you can talk about path connectedness, whether there are rectifiable path in a space, how many, so this is a vague way of asking, how many rectifiable path or curves. So usually we will stick to the word path rather than curve. Does X have? So this purely being a rectifiable curve has nothing to do with measure. It only deals with this distance function. Another one is whether our space is path connected. Given any 2 points, can we just find some path between the two? If X is union of 2 parts, then this fails. Another more important quantitative connectedness property is our space quasi-convex? So, what is quasi-convexity? In Euclidean space, given any x and y, their distance is length of one particular path connecting them. If you are working in subsets of Euclidean space, if you take this to be your space X, then this is no more correct, because if the space is not, if this set is not convex, then this shortest path no longer exists. So you're still talking about this X equipped with the Euclidean distance. So distance of this and that is still the length of this straight line, but there is no shortest path within omega connecting them. So a shortest path maybe looks like something like this, but still their length is not equal to dxy. However, in my picture, for example, you see that given any 2 points, maybe there is a path not that much longer compared to this distance. So this says if we say a space is quasi-convex, and this again is just a metric property, you can discuss this without any measure. So you say there exists some constant c, which will necessarily be more than 1, such that for every x and for every y, there exists rectifiable path from x to y with length of gamma. This is always more than the distance of endpoints. This is just by definition of length. But now we say that this is less than c times xy. So if you allow this multiplicative help, then you can always find path. So we will see, for example, later that spaces that support Poincare inequality are necessarily quasi-convex spaces. So that's an indication that this quasi-convexity is very important. Stronger than quasi-convex is a space being geodesic. This would mean that for every x and for every y, there exists some path from x to y such that the distance of x and y is exactly equal to the length of gamma. So convex subsets of Euclidean spaces have this property. Somewhat weaker than geodesic, but very close to it. So this is stronger than being quasi-convex, but weaker than being geodesic. So for every x and for every y, there isn't one path which realizes this dxy. So if you say that this is length of gamma, this would be geodesic. But then you say, okay, there isn't any such, but also you can get infinitely close. So infimum over all gamma. So let's say infimum of length of gamma over all gamma that join x to y. So here, the famous example would be you have your Rn and then you remove just the center. Then if you have x and y on opposite sides of this origin, the shortest path giving you x minus y would be the straight line, but that is not a path inside your space. You have to always avoid this origin, and whenever you avoid that origin, you pay some price. So each time length of gamma is strictly bigger than distance x minus y. However, given every epsilon, you can make it so that the length also is not that far away from being equal to x minus y. So from picture it's immediate. So length space, almost geodesic. With geodesic space, you have dxy equal to minimum and not infimum of this same set of length. Okay, so we're looking at list of properties that concern only the distance on a metric space. So being connected, having rectifiable path, being path connected, being quasi-convex, being geodesic, being a length space. There's also this notion that once you have path connectedness of a space, you can forget your original metric and then out of this construct length distance, or the so-called intrinsic distance. So when you measure the distance from within the space, so in my Euclidean example, this would mean that forget that you are sitting in the Euclidean world. Measure of the distance of these 2 points is the shortest distance with path within this region that you can build. So once you switch from original distance to this intrinsic distance, you immediately become a geodesic space. And if you have, for example, properness and completeness of space, then often it actually upgrades to geodesic, because often you can make sure that this infimum is actually a minimum. This idea comes up a lot. So some properties, the class of suitable functions will have a certain behavior if you equip this subset with the Euclidean space and the same measure, say the Euclidean L2 measure, versus if you have the intrinsic distance and the same measure. So these are totally different spaces in general, and the behavior of suitable functions on one of them could be different from behavior of suitable functions on the other. Okay, also notice that the class of Lipschitz functions is defined through the notion of distance. Okay, so this was kind of an overall of the objects that we will be looking at, and also the kind of properties that some theorems will assume, or properties that will appear in the conclusions of theorems. One such theorem I already mentioned: if you have Poincare, then you are quasi-convex, which is quite a strong result. So for the future videos, for some time, all our focus will be on triples of a metric space equipped with often a Borel measure, and plus choose your properties. So choose properties for D and for this mu. I'm sorry to drag this too long, but sometimes things are so often repeated and we get so much used to that we don't even think twice about. So for example, I mentioned the notion of X, the space being complete. So this being complete here has nothing to do with the measure or being a proper, later I will define this, a proper metric space or being a compact metric space, and similar ones rely only on D and not the measure. Okay, so again, this video is an overall picture of what is happening, but it's also important because once we get into the details and technicalities, it is important to separate what we are requiring of the distance and what we are requiring of the measure, and also how they react and connect to one another. So what is next in our agenda? To be able to talk about sublable functions on general metric measure spaces, we have to definitely talk about a notion of path integrals. So we have to be able, this is the crucial notion at the heart of our definitions, of how you integrate a function, often a Borel function, on a rectifiable path. What is meant by this? And once we have this, we will talk about modulus of path families. This will be a way to talk about large versus small family of path. Or especially important will be our notion of negligible collection of path. So we will require some inequality, say for all G gammas, but we also pardon a small collection of gammas. So we will say that this holds some property, let's say this is, I don't know, bigger than 1 holds for all rectifiable path, but as often is the case with anything measures theory, we want to always allow negligible sets. So we want to be able to rigorously talk about some property holds for all gamma, say rectifiable, except for a negligible collection. And this negligible is where we bring in the notion of modulus of path families. With these two notions in hand, we really are ready to define Sobolev spaces. So we can define, and I must say this is just one way of defining Sobolev functions, one class of Sobolev functions, which we will be denoted by N1P space on X. And after talking a little bit about these, we will be able to also talk about different classes of Sobolev functions, for example, the high-wash Sobolev space. But I will hold on maybe on that one, because once we define these Sobolev functions, it doesn't mean that these give us any interesting class of functions in general. So we will have to talk about under what conditions result in N1P being interesting. So interesting would be, for example, that they are more than just integrable functions. They really have derivatives in a strong, in some sense that is not trivial. And here is where comes this mu being doubling. The nicest spaces where this theory becomes really interesting is when you have a doubling measure and when we have the so-called Poincare inequalities. So these are the two key notions that allow one. So these are the key notions that if you assume, then the space that you construct, this Newtonian space, will be an interesting class of functions. Okay, so if you have any questions, please put them in the comments. I know this became a long video, but also the notions I had discussed also before, so hopefully not an avalanche of information there. And also if you feel not comfortable with this much material in one video, remember that we will review them as we go and when time comes to do the specifics. Thank you so much and have a great weekend.